Data from suncalc do not make any sense on a flat Earth, and they do on a globe model. A lot of people use websites like suncalc or mooncalc and applications like Stellarium or Solar System Scope, and they use it to know at what time they can see the sun set and rise, or just to know where the sun or any other celestial body will be at a particular time of the day or night. And apps are used by amateur astronomers to know where to point the camera, and they always find it at the predicted spot in the sky. Suncalc is used in a number of debunking videos on both sides, and I've never heard anybody doubt the validity of the data. And that amazes me because it's in a mathematical model behind those sites that can predict those exact figures. And if flat Earth believers accept the data, why not all of the data? The app gives both azimuth and altitude of the sun, and the angle is negative at night. Right there. And working on my other video on how data of the position of Uranus does not make any sense on a flat Earth and makes total sense on a globe Earth, and inputting all the data by hand, I thought this is too much manual and boring work, so let's see if I can program something to do it for me. And I found Kepler's laws of planetary motion and one simple formula to describe it all. And programmed this into an app that visualizes the data gave me the possibility to let me, and now you, see some patterns, like you see on the screen now. And where a single item of data is just that, a pattern shows the logic behind the data. And there are a few nice examples that do not make sense at all on the flat Earth, but you will see the beauty of the simplicity of the formula and how it makes total sense on a globe Earth. And yes, I went a bit over the top to make this application, so not only did I program the comparison app, but trying to understand the definition of hour angles and right ascension and Greenwich Mean Sidereal Time, and even deeper trying to understand what makes Kepler's formula work and explaining things like the argument of periapsis and the difference between mean and true anomaly, and finally the laws of planetary motion themselves. I created some other models to visualize it, and I will go into further detail on those sides in one other video. But before we go into the examples, let's find out if my data from the formula matches suncalc, shall we? Okay, so let's look at some examples. So this is the same date, same time over the planet. And what you see is that even with a single beam, it doesn't make sense. Because right now, the sun is up. And it goes below the flat Earth, and it's going in a circle. Really, that is what you see with a single beam. That's what you see at globe Earth, because it's always pointing at the same position in the sky. Let's make it a bit more complicated. So let's put it on the prime meridian and put a fixed sun position, so the sun is always in the same direction and a bit quicker. So again, this is the same date during the day, so it's going through a 24-hour period over all these places on the Earth. So every single shot is where the sun is at that time. So what you see now, it's going on the below, and then it's suddenly appearing on the other side, right there. So everybody on the top half of the flat Earth is seeing the sun right here, and then 1 hour later, they see a double sunset over here and over here. But they will see the sun at the same spot on this part and just below, but not in between. And then it flips instantly. That is within 1 hour. It moves from one side of the globe, from the flat Earth, really, to the other side. That doesn't make sense, does it? And here it goes again. It's setting in the bottom half and appearing in the top half. Cool, isn't it? Okay. An even better one. Okay, let's fix the sun position again. So what we have right now is, again, it's the same time, same date, different places on the Earth, and this is where the sun is at that time. Nice. On the globe Earth, one direction, one sun, everything pointing in the same direction, while on the flat Earth, the sun is everywhere. The sun is here and there and there and there and there and there. The sun is setting on the rim, and the sun is below, but it's the same sun. It doesn't make sense. So what happens when you gradually do it? It has to do some calculations now, because it's pretty heavy. This is during 1 hour, just 1 hour. Let's fix the sun again to one spot. So the Earth is turning slowly, and while it turns, it's getting light. You see the sun rising. When the lines are red, it's a low red sun, of course. And let's look at the flat Earth. So 1 minute. This is 1 minute. 1 minute later. Like that. It's going over the Earth. You see the sun setting and rising, but where is it? And I'm not even talking about the night, but the sun, the angles, they're pointing everywhere. Where is the sun in this picture? Can you tell? It doesn't make sense. While looking at the globe Earth, do you see how beautiful it is? How elegant? And this is one single mathematical formula that predicts, that shows how the sun can be seen from any place on the Earth. Okay, just one other one. I call this the porcupine spots during 1 day of the month, and it's showing the seasons. It's a full picture. So it's May, and the next scene it will be June, July, etc. And it's January again. So in January there's a wide outspread of the sun at this time. It's 6 o'clock UTC. Dark on the right hand side, and it's light on the left. And when we go into the summer, the sun is getting concentrated. You see, if it's a local sun, it should be here somewhere. And when we go into winter time, it's spreading out. So this sort of might explain why it's colder in the winter. However, when we move a bit earlier in the day, you will see the same. It's concentrated in the summer, and it's spread out in the winter. And that's not what we see. It's not the same temperature everywhere during the year. So it's called a porcupine because, well, you can tell. Oh. The sun is everywhere. And it's totally beautiful on a globe Earth. That's still the Earth. So let's get a bit sciencey. A bit because I'm not an astrophysicist, it's just a hobby. And building this model, I got to learn more and more, but I do not claim to understand it all. But this is the Earth going around the Sun, and yes, the Earth is not spinning, and the Sun is, because the Sun is spinning every 25 days. And the Earth is fixed because it's programmed like that. But what you can see is that the red is the true circle and the green is not. It's slightly off center. So how does this work? Well, Kepler, of course. Kepler is my new hero. 1600, that's when he thought of this. And what he says is that the orbit of a planet, Copernicus thought it was a circle, Kepler thought it's an ellipse. And the Sun is not at the center, it's just at a focal point of the orbit. So does that mean it's not in the center? It's right there. So the Earth is going around in an ellipse, just slightly off center. Then the speed is not constant. The speed is area speed is constant. So this area is just as big as that one. So what does that mean? So we have these three laws, but how do you calculate the position of the Earth around the Sun and make pretty pictures like this? You see the Earth tilting around the Sun while moving in its orbit. Okay, so I can show you by showing you the Kepler areas. So first of all, let's move the Earth a bit off center, or the Sun off center from the Earth, so it's more of an ellipse, an exaggerated version of the Earth's path. And I will show you the Kepler areas, and those are these gray areas over here. So the Sun is not at the center, it's in a foci of the ellipse, and the gray areas are painted right here. And what Kepler's law said, okay, the Sun is not in the center, and it's an ellipse. Okay, let's put a nice circle, and you see it is an ellipse. And the Sun is moving, or the Earth is moving faster on the left-hand side, and it's slowing down the further it gets away from the Sun. But the time it takes to cross this little area is always the same. And that is the law of Kepler. But this law is just 3 lines. How do you get from these 3 lines to calculating the position of the Earth? And that's where the Keplerian elements. So what he did, there was 6 items that you have to specify at a specific date, and then you can calculate from that what the true position is right now. So it's the shape of the ellipse, that's what we changed just then. The axis, so how big and how small the ellipse is. The inclination, which is 0 for the Earth because we are in the plane of reference, because that's us humans. The longitude of the ascending node, which is actually one point from where everything is calculated. And the argument of periapsis. Actually, that's the position. And let me see if I can show you argument of the periapsis. There's this one line where the Earth is closest to the Sun. And finally, the true anomaly, or the angle. Because it's hard to calculate the true anomaly just like that over time, they use the mean anomaly. And that's a convenient angle which varies linearly with time, which says it's always the same when going through the time. You can see the mean anomaly is going very slowly, but it never varies. It's just the same amount of angle for every day or every few days. Well, the true anomaly, it is the light yellow, it changed. It's slowing right now, while the mean anomaly is faster, and the closer we get to the closest point and to the Sun, you see it changing rapidly, more rapidly. So the mean anomaly is easier to calculate, and from the mean anomaly you can calculate the true anomaly. So we've got Kepler's laws of planetary motion, and we've got the orbital elements. And finally we've got Kepler's equation, and this is it, as simple as that. The problem is that we have to calculate E instead of M. That's slightly pain because you cannot just calculate it, you have to sort of approach it. So this is the first calculation, and then you go through a number of iterations to get closer to the truth. But this is it. 2 lines of code. And you get this. This is beautiful. Nice. It explains it all. And this is beautiful on the right. But porcupine, I don't get it. How can this be the truth? If you want to know more about how to calculate the Sunangles, I will go into another video to explain sidereal time and what you need to know about right ascension, etc., etc. But for now, thank you for watching, and I hope you enjoy.